talk today about the hypoelliptic Laplacian, putting myself a little bit in the position of a traveling salesman, trying to sell this theory and this particular operator, while not being entirely sure that it's a totally useful thing in terms of practical methods. However, I will try to show to you that in some sense it reflects something which exists and which is, I believe, rather deep. So the idea in some sense is to produce a theory which will interpolate between Hodge theory and the geodesic flaw, and more or less between the Hodge theory and any dynamical system. The inspiration for this comes from path integrals. So I will allow myself to speak about things which do exist, but also about things which do not exist. These things which do not exist playing the role of some dream. And eventually you will see that at some point the dream comes true, and you effectively produce some new gadget, some new object out of this dream. So I will briefly review what is Hodge theory and the so-called Witten Laplacian. Then I will explain what is the so-called Witten localization and functional integral. I will give the construction of the so-called hypoelliptic Laplacian. I will explain how it interpolates in a certain way between the ordinary Hodge theory and any dynamical system. And then I will give some results about the analysis of this Laplacian that we have obtained recently with Gilles Lebeau. So first of all, classical Hodge theory. So I start with a de Rham complex. So you give yourself, say, X, compact Riemannian manifold. You give yourself also a complex flat vector bundle equipped with a Hermitian metric. So if you like, for the moment, you can think of F to be simply C. So you consider the de Rham complex of forms on X with coefficients in F, where dx is the de Rham operator. So as you know, you have dx squared is equal to 0. And you can consider the cohomology of this complex, that the cohomology of X with coefficients in the local system F. So H of X and F is a Z-graded finite dimensional vector space. So what is Hodge theory? Hodge theory is a way to represent canonically cohomology by explicit differential forms. So given the metrics on X and on F, you can introduce L2 Hermitian product on differential forms. And then you can construct the formal adjoint dx star of dx with respect to this L2 product. You form the so-called Laplacian, which is, if you like, the square of dx plus dx star, or maybe you're more accustomed to see this as the anti-commutator of dx and dx star. So this is a second-order elliptic operator. And the basic result of Hodge theory tells you that the kernel of this Laplacian, these are called the harmonic forms, you can identify it with the cohomology of the vector bundle F. So in other words, the forms in H in the kernel of Laplacian are closed, anchor closed, and any cohomology class is represented uniquely by an element of the harmonic forms. So I will briefly explain what is the Witten twist, which plays an important role as an inspiration for what I'll do later. So the idea of Witten was to try to connect, in some sense, Hodge theory with Morse theory. So the way he did this is as follows. You give yourself F to be a smooth function from X into R, and you twist the de Rham operator dx. So you twist it by the exponential of t times a function. So this way you have a family of de Rham-like operators dxt, whose cohomology, of course, does not change with t. It's canonically identified with the original cohomology. So in such a situation, you can again introduce the formal adjoint of the twisted de Rham operator. So you get a new adjoint. And of course, this way you also get a new Laplacian, which now depends on the parameter t. Let me observe that for t equal to 0, this is simply the original Laplacian. So in other words, the Witten Laplacian gives you a deformation of Hodge theory. Now, what happens actually in Witten's theory is that when t tends to infinity, there are a number of things which happen. So in particular, well, I will describe it briefly, that the spectrum of the Witten Laplacian, Laplace xt, splits into two pieces. So most of it goes to plus infinity. And there is a finite dimensional piece which goes to 0. This isn't the case where f is a Morse function. So among the part of the spectrum which goes to 0, you have the part of the spectrum which is exactly 0. So this corresponds to the harmonic forms. And you have some eigenforms associated with eigenvalues which are exponentially small when t tends to infinity. So all of this forms a finite dimensional, if you like, vector space which moves with t. But the point of Witten's theory is that when t tends to infinity, actually the small eigenvalue eigenforms concentrate near the critical points of the function f. Concentrate near the critical points. So in other words, from these small eigenvalue eigenforms, you have a certain analytically defined complex, which is a complex of small eigenvalue eigenforms, which is identified in a way with the critical points. And this way you get, for instance, very quickly an analytic proof of the Morse inequalities. Just from the historical point of view, let me also mention that if the gradient field nabla f is more small, you can actually identify the complex of small eigenvalue eigenforms with the Morse small complex of the gradient vector field, at least under natural transversality conditions. So this was proved by Elfer and Sjöstrand, and later on I rederived with Zhang Weiping another proof in which, in particular, we also proved the equality of analytic and Riemann-Wester torsion this way. So now what I shall ask is the following question. Can one replace the manifold X by its loop space? So Lx here is a set of smooth maps from S1 into the manifold. And you ask yourself, is it possible, first of all, to construct a Hodge theory on the loop space? And second, is it possible to develop the context of Morse theory and Witten localization so that you would interpolate between Hodge theory on the loop space and critical points of Morse functions on the loop space? So I will give two answers. The first answer is no, you cannot do that. So first of all, one of the reasons why it's very difficult to do it is that Hodge theory actually is almost impossible to construct on the loop space. That is, you effectively have a de Rham operator dLx, but the construction of the adjoint is extremely difficult. I mean, just because of the definition of the L2 Hermitian product, I mean, there are many technical difficulties, which means that for the moment, there is no reasonable Hodge theory on the loop space. Okay, the Laplacian would have to be an infinite dimensional operator, and essentially for the moment, although we know to do a few things, we do not know how in effect to develop Hodge theory on the loop space. On the other hand, I will say yes, because the Morse theory aspect of the loop space exists. You can effectively develop Hodge theory on the loop space, Morse theory on the loop space. In particular, for instance, for one basic functional, which is the energy functional. If you take a loop, you just take its energy, E of x, and for instance, this functional, well, you know that its critical points are the closed geodesics. And Morse theory has been used in a variety of contexts on the loop space, in particular by Bott in his proof of Bott periodicity. So you have a sort of catch-22 situation in which one of the things you want to start from does not exist, but the target thing, which is the Morse theory, in some sense exists. And what I'll try to show is how, in effect, to construct some shadow of this Hodge theory on the loop space in our existing world. So the question is how to connect the non-existing Hodge theory of the loop space and the so-called invariant Morse function on Lx. So why do I mention invariant? It's because on Lx you have a natural action of S1 simply by rotation. If you take a loop, you can rotate it, and we will be interested essentially with S1 invariant functionals, the energy being a typical such S1 invariant function. So the way we will do this will be via semi-classical analysis on Lx. So what do I mean by this? So I certainly know that again, the Laplacian on Lx, I even introduce a parameter t here, does not exist. But let's pretend that it does. So to pretend that it does, maybe we have gone to some restaurant and drank a little bit, maybe more than we should of caipirinha, but I will try to show you actually that caipirinha in some sense is playing a very fundamental role in this theory. So what you will try to do is, okay, this Laplacian does not exist, but let's pretend it exists, and let's construct its heat kernel. Now, what the heat kernel does is that, as you know, it's connected with Brownian motion. Okay, so the heat kernel describes more or less the way that when you start from one given point and you propagate the point using Brownian motion, how does this probability distribution starting from the Dirac mass diffuses? So the mental picture that you should have is that you start from a loop here and you propagate the loop as a sort of Brownian motion inside of the loop space. So if you like, what I'm describing here is, in some sense, the propagation of a string. Okay. But I never forget, in spite of the fact that I drank maybe too much, that this theory does not exist, the Laplacian does not exist. So what I do is that I make this time, this is a time of propagation, and I make it very small. And I hope to be able to construct something which will be the shadow of this theory, simply because when you propagate, you use the heat kernel, and you look at its small time asymptotics as the time here, s, the time of propagation, tends to 0, you will recover something which will live on the loop space, and which we will eventually describe through differential operators on the manifold itself. So this, we have to think a little bit. Again, I take my loop, I propagate it a little bit using Brownian motion on the loop space, but actually, since I cannot propagate, I do this infinitesimally. And when doing this, what I try to recover is some germ of this Hodge theory, which I will eventually describe using differential operators on the manifold, and more specifically, on the cotangent bundle. So notice here that I have the parameter t. The parameter t will come from a certain Morse function, or some smooth function on the loop space, like the energy. So this means that we will produce actually a whole family of differential operators on our original manifold, which in some sense will be the shadow in the sense that S is very small now, of the true Hodge theory on the loose space. So how can we do this? So first of all, to effectively do this, what I'll try to do is understand how does the Witten deformation works from the point of view of the path integral. Okay, so one reason for this is that path integrals, first of all, are very interesting by themselves, but that physicists have taught us that behind the path integral, or underlying it, there is a certain cohomological formalism. And in effect, by working on the path integral language, you will see that there are very natural things that you can do in the path integral language, natural from the point of view of cohomology theory, and which are not natural at all in the small world in which we live. And so by understanding effectively the geometry of the loop space, we will be able in some sense to produce in our real world what effectively it's almost entirely clear from the loop space point of view. So what our first step number one is why is Witten localization takes place from the path integral point of view. So let me observe that if you give yourself a smooth function on the manifold X, it lifts naturally into a smooth function on the loop space, which is simply obtained by integrating the function integral of 0 to 1 of f of xt dt. Now, I just interrupt myself a little bit, and I want you to think of this as some part of a Lagrangian. Okay, as you know, when you have a dynamical system, a physical dynamical system with Lagrangian, it is usually made of two pieces. One piece is the energy, and the other piece is the potential. And what I want you to think of this function f is just a part of a Lagrangian in which actually the most important part has been forgotten. And in some sense, what I shall do is resurrect this Lagrangian à la recherche du Lagrangien perdu, searching for the lost Lagrangian. So I'm saying that in the functional integral representation of the standard heat kernel of X, that is via classical Brownian motion, Witten's localization can be understood via the so-called multi-equivalent Thom forms associated to the function f. So notice that there is Witten, multi-equivalent, and Thom, which is probably too much. So let me try to make it as simple as possible. So what are the multi-equivalent Thom forms? Well, actually, the multi-equivalent Thom forms were already introduced by Chern when he proved the Chern-Gauss-Bonnet theorem. So let me just explain briefly what is the Chern-Gauss-Bonnet theorem. That's just writing the Euler characteristic of a manifold as the integral of the Euler class of the manifold, the Euler class being represented by the Euler form in Chern-Weil theory, using the Pfaffian of curvature. So what are the multi-equivalent Thom forms? If you give yourself a vector bundle with connection, metric and connection, you have the Thom class of the vector bundle. So the Thom class, I will not explain what it is. I mean, it's, well, it relates the cohomology of the total space of the vector bundle, the compactly supported cohomology of the total space of the vector bundle, to the cohomology of the manifold. But in practice, what it is a cohomology class on the total space of the vector bundle whose integral along the fiber is equal to 1. Okay, more or less, you can say that's the definition of the Thom class. The Thom forms are a canonical way of representing the Thom class. So it is a closed form of the total space of a vector bundle, and it is actually a Gaussian-shaped differential form on the total space of the vector bundle. And we know that the integral of the Gaussian is actually equal to 1, properly normalized. So actually, Mattei and Quillen were able to cook up some form. I will not give the explicit formula here. I just give the leading term, the term of degree, I mean, that's the simplest part, which is this Gaussian. So this is a canonically defined differential form which represents a Thom class. Now, the use of this Thom form is that it allows you to prove, for instance, something like the Hopf index theorem, which relates the Euler characteristic of a manifold to the index of the zeros of certain sections. So actually, if you have a section of the vector bundle, say Tx, you can pull back the form on the total space of the vector bundle by the section. So this way, you get a form which on the manifold X, on the original manifold X, which looks like exponential of minus t squared y squared over 2. You see that when t is equal to 0, we just recover the form 1. But when t tends to infinity, this form localizes on the 0 set of the section Y. So you do have this interpolation mechanism. Actually, what you can show is that as a current, it concentrates on the current localized at the 0 set of the section Y, and so it gives you a proof of Chern-Gauss-Bonnet. Now, the extraordinary things that physicists taught us is that there is an infinite dimensional version of this Gauss-Bonnet, Chern-Gauss-Bonnet theorem, and that there is, in the path integral formalism, something like infinite dimensional Thom forms. So let me give you an example for this. I start from the so-called Mackin-Singer formula for the Euler characteristic. So this is a well-known formula in index theory, which allows you to express the index of an elliptic operator as the trace or as the difference of traces. This is supertrace of the heat kernel. So this is a very easy formula. You start from this formula, Euler characteristic of X is equal to the supertrace of the heat kernel for the, let's say, for the twisted Laplacian, twisted Witten Laplacian. So the way that physicists taught us how to interpret this is in terms of path integrals. Okay, so path integrals, we think of them as being integrals of infinite dimensional measures, actually of measures on loop spaces. What physicists have taught us through supersymmetry is think of these measures not as measures, but as differential forms. In other words, they force us to think of these measures as being forms of infinite degree, which of course for us is difficult to think of. But anyway, they taught us that even if we mathematicians have difficulties to think about them this way, that's the way the world is, and we cannot do anything about this. And so actually, the way that physicists write the formula I wrote before is not as a classical path integral which exists in our world, which would be the classic path integral, well-defined integral of a measure. But they force us to think of this integral as an integral of a almost closed differential form on the loop space, which is a wedge product of two guys. So one part is a form alpha, it's a universal one, and it essentially contains the energy of the loop. And the second part is exactly the Thom form I mentioned before on the associated to the tangent space to the loop space, but you take the pullback by t times the gradient of f, where f is the integral of our little f. Okay, so let's think again. Forget about the alpha for the moment. Just look at the second term. So this second term, which I wrote as t nabla f star of phi of phi, I can write it as exponential of minus t squared gradient of f squared over 2 plus something. Again, you see that when t tends to infinity, this exponential will localize on the 0 set of the gradient of the function f, large f. If the function little f is Morse, these critical points are exactly the critical points of the original function. So in effect, from the path integral point of view, we have given a cohomological explanation of why does the Witten-Hodge theory interpolates between classical Hodge theory and something which localizes on the critical points of the Morse function. The idea underlying this is that the mechanism is just an infinite dimensional version of Chern-Gauss-Bonnet theorem and its relation to Hopf index theory. This is just for the classical Witten deformation. Now, the idea is simply to try, as I say, to resurrect this lost Lagrangian and to say, I just forget about the Morse function little f for the moment, and I replace it by the energy integral of half of integral of 0 to 1 of x dot squared. Of course, I could combine the two and get an effective generalized Lagrangian, an effective Lagrangian in the physics sense. Now, again, observe that the gradient of the energy is simply minus the second derivative of x. And so, if we think from the point of view of the path integral, what we're trying to do is simply, in the formula I gave before, is to look at the formula which looks like this. Again, alpha, wedge, t, nabla, e star of 5. What I did is simply I replaced f by e. I'm sorry, I go in the opposite order of the natural alphabetic order. In the previous formula, I just replaced f by e. So if I do this, how does our path integral look like? How does it look like? I again have integral over the loop space of exponential of minus the energy. And then I have a second term, which is simply t squared, as I say, t squared of the gradient of e to the square. So the gradient of e being x double dot, the gradient square is x dot double dot square. So in some sense, I want to produce a formula which will express the Euler characteristic of any manifold as the integral of a path integral which looks this way. Observe for the moment that I still do not have any deformation of Hodge theory which will correspond to this formula. And in some sense, the purpose of my talk is effectively to produce this deformation. But to understand how to produce it, I need, first of all, to understand very precisely this formula. So actually, forgetting about all these small dot terms which contain all the complicated differential form aspect of the formula, what I can try to do is simply interpret what is the dynamics of a path which is submitted to, which is governed by this path integral. So a path integral, again, think of this for a moment, again, as a measure on the loop space. And what we want to understand is what is the probability law of the path x under this measure. So if we use classical, say, so-called stochastic calculus, what we see actually is that the dynamics of the path x can be described in two ways, either as a first-order differential equation of the cotangent space. So I wrote it as x dot equals p, and p dot equals 1 over t minus p plus w dot, where w is the Brownian motion. So that's the first description of this measure. The second description of the dynamics of the path x under this measure is through a second-order differential equation. X double dot is equal to 1 over t minus x dot plus w dot. And this is the thing I want you to remember for the moment. Okay. So notice here that the equation is of order 2 as well as is the equation of the geodesics, which is also an equation of order 2. So this is not an accident. So now I'm almost done in terms of constructing the deformation of Hodge theory. Because there is, in effect, a sort of mechanical way, once you have a path or, let's say, a Markov process, which is described by a dynamics of this kind, there is a certain way of associating to it a differential operator. Now, this differential operator describes the dynamics of the motion. Actually, it will be dynamics now which lives on the couple xp. Note that the first order differential equation I wrote before was in the variables xp. The differential operator is now actually, which describes the dynamics of this path, is actually an operator which is of second order. It has two pieces. It's essentially an harmonic oscillator along the fiber, and it has also an x component, which is this nabla ptx. This, you should think of this term as being the geodesic, the generator of the geodesic flow on the cotangent bundle. So if you like, it is the Hamiltonian vector field on the cotangent bundle associated to the function p squared over 2. So the question I ask now, is there a way of constructing a new Hodge theory on the total space of the cotangent bundle in such a way that the Laplacian of this new Hodge theory looks like this? So before saying more about this construction, note that this operator is not elliptic. It is not elliptic simply because it doesn't have a second order term in the x direction. It's second order in the p direction. It's just first order in the x direction. So it is not elliptic. It is not self-adjoint. The harmonic oscillator is self-adjoint. The generator of the geodesic flow is q-adjoint. So this means that if such a Hodge theory exists, we're actually destroying the whole ideological basis of Hodge theory. We destroy self-adjointness and we destroy ellipticity. So let me try to explain how this construction can be done effectively. Now I totally forget about path integrals, and I will show you how to produce this operator as being a Laplacian associated to some exotic Hodge theory. So what I will exploit is this, of course, the existence of the symplectic structure on the cotangent bundle. So you look at the de Rham operator on the cotangent bundle, d t star x, and I note that t star x is, of course, a symplectic manifold. So once you have a symplectic manifold, you can introduce the symplectic adjoint in the same way that when you have a metric, you have the L2 adjoint, you can introduce the corresponding symplectic adjoint. Now, the point about this construction is that if you construct the Laplacian, you have the operator D, its symplectic adjoint, you get actually, as a Laplacian, you get 0. Now remember, we wanted to produce a Laplacian which was hypoelliptic, but not 0. So that means that we have drunk maybe a little bit too more of caipirinha again. We have gone too far in the hypoellipticity direction, but in some sense, we are already in a better shape because in effect, we have produced something which is 0. So actually, what you have to do is, first of all, think about what you're doing. So I'm sorry, I have to skip this. Actually, the effective construction goes this way. You use the Levi-Civita connection to split the tangent space bundle to the cotangent bundle. So the tangent bundle to the cotangent bundle, you split it as a direct sum of a vertical tangent bundle and horizontal with respect to some connection. On this total tangent bundle, you introduce a Billiner form, which is neither symmetric nor antisymmetric. It has a symmetric part, which is just the Riemannian metric on the base, and it has another part, which is a symplectic form. You also do some Witten twist. So you introduce some Witten twist where now the Hamiltonian p squared over 2, or more generally, any Hamiltonian could come in. And then I give you what is the formula for the corresponding Laplacian. So this is the Weissenberg formula for the corresponding Laplacian, which is the analog of the classical Weissenberg formula. So the formula tells you that the Laplacian for this exotic adjoint structure, it is exactly of the kind that I mentioned before, in the sense it has two terms, I mean, there's several terms, but you recognize the first term is the harmonic oscillator. The last term is the generator of the geodesic flow. And there are some intermediate terms which are just curvature-like terms, which are, of course, very important. But in some sense, from the symbolic point of view, they are irrelevant. So we have produced, in effect, our new Hodge theory. Now, once we have done this, notice that this Hodge theory depends on the parameter c, and c should be thought of as t here. So c is equal to t, or maybe 1 over t. C should be thought of as 1 over t. So, first of all, when t tends to infinity, so what I'm saying. So, what I will show is now this Hodge theory interpolates between classical Hodge theory and the geodesic flow in the same way as the Witten Laplacian interpolates between classical Hodge theory and something which localizes on the critical points of the given Morse function. So just to remark here, I observe that this operator is hypoelliptic in the sense of Amanda. This plays a fundamental role in the analysis of this Hodge theory. Just a point before going into a little bit more details, let me look at the dynamics again of the path x under this measure. So I wrote the equation, the second order equation, as being x double dot divided by c is equal to minus x dot plus w dot. Let me show you first that at the dynamics point of view, these dynamics interpolates between Brownian motion and the geodesic flow. Brownian motion being itself associated with the Laplacian, which is Hodge theory. So I claim, first of all, that from a dynamic system point of view, this effectively interpolates between the two dynamics. So actually, if you make c equals to infinity, you get the equation x dot equals w dot, which is the equation of classical Brownian motion. When you make c equal to 0, you get x double dot equals to 0, which is the dynamics of the geodesic. So already, from a dynamical system point of view, I've produced a family of differential equations which naturally interpolates between the two dynamics. Now, what is true is, of course, much more that at the operator theoretic point of view, the Laplacian that I produce when c tends to infinity, or if you like, t tends to 0, converges to classical Hodge theory, and when c tends to 0, it converges to the generator of the geodesic flow. So how is this possible? So just briefly to describe what happens when c tends to infinity, you actually can write the Laplacian, which is an operator now on the cotangent bundle, as the sum of two terms by some rescaling, c times a plus square root of c times b, where a is the harmonic oscillator along the fiber. What happens is that when c tends to infinity and you look at the corresponding eigenforms, you force localization on the kernel of the harmonic oscillator. So localization on the kernel of the harmonic oscillator more or less is equivalent to using some Leray spectral sequence argument, which makes that actually you forget totally about the total space of the cotangent bundle, only recover the base manifold itself, so that it is true. You can make it precise that when c tends to infinity or t tends to 0, your operator on the cotangent bundle converges in the appropriate sense to the Laplacian on the base manifold. This is step number 1. So effectively, our theory is a deformation of classical Hodge theory. Now, when c tends to 0, you just do another simple rescaling, which shows to you that when c tends to 0, the operator R Laplacian more or less just looks like essentially like the generator of the geodesic flow. So in effect, our family of Hodge series interpolates in the appropriate sense between classical Hodge theory and the generator of the geodesic flow, and more generally, the generator of any naturally defined, in the physics sense, dynamical system on the cotangent bundle. So there are many aspects to the analysis of this new Hodge theory. First of all, because the operator is no longer self-adjoint. It is actually almost as self-adjoint as possible for something which lives on the cotangent bundle. I will not explain to this. You have to take into account the involution of the cotangent bundle. P gives minus P. If you take this into account, then the operator becomes self-adjoint. So what can you say about this Laplacian? So first of all, it has a discrete spectrum, which is conjugation invariant. The spectrum is no longer real, but the spectrum is conjugation invariant. So the Hodge theorem almost holds. So what means almost? It means that for classical Hodge theory, you know that the harmonic forms exactly represent the cohomology. For this deformed Hodge theory, the harmonic forms are simply the first term in some spectral sequence. Okay, so you have the kernel of Laplacian, and inside of it, the cohomology sits. But it's not true anymore that, in effect, the Hodge theory holds. The heat kernel is smoothing and trace class. There is a corresponding so-called local index theory. So local index theory is a gadget which, in particular, allows you to prove, say, either Chen-Gauss-Bonnet from the Hodge theoretic point of view, or more generally, to prove the Atiyah-Singer index theorem. So the basic result that we have proved is that actually the Ray-Singer torsion of the hypoelliptic Laplacian, so the Ray-Singer torsion is a spectral invariant that you construct via zeta function, or derivatives at zero of the zeta function, is essentially equal to the Ray-Singer of the original elliptic Laplacian. So I want to conclude on this. There is a well-known conjecture by Fried, which relates actually so-called dynamical real zeta functions, which conjectures actually certain gadgets that you can cook up from real dynamical zeta functions, is equal to something else that you can cook up using the classical Hodge theory. Okay. So in this framework, if you just formally extrapolate what is known about more classical Morse theory and so on, you realize at a formal level, this conjecture of Fried is just a consequence of the so-called Shiger-Müller theorem, which says that the Riemann-Messer torsion and the Ray-Singer torsion are equal. In some sense, if we take our result, which says that the Ray-Singer torsion of the hypoelliptic Laplacian is constant, doesn't change, when moving the value of the parameter to the parameter C to 0, we'll get closer and closer to the closed geodesics. And eventually, what I hope we will be able to prove is that actually this family of Hodge theories are exactly a construction of what's called in dynamical system theory the transfer operators via which the real dynamical zeta function is itself constructed. Thank you very much.
I'll give you just two of them. I don't see here colomorphic, anti-colomorphic.
No, because you have, yeah?
I think it is just the RAM theorem.
Well, it is Hodge theory in the sense that you represent the cohomology by harmonic forms.
Yes, it is in the RAM theorem. In the RAM box, you see all the
No, this is Hodge. This is Hodge theory. No, this is called Hodge theory. They represent the fact that the RAM theory can be represented via harmonic forms. This is Hodge theory. But there is actually a complex version. If you're happy with a complex version, there is a
representation of homology by manifolds in the book by the Ragni. This is what we call the Ragni theory, but not the Ragni theory.
Is it?
And the second question is more complicated. The Ragni theorem is just a bridge between two approaches to calculate now between two definitions of the topology associated with many. This almost existing theory is a bridge between two theories. Well, this existing theory is a bridge between two theories, which carefully work.
So,
Does the homology of the loop space?
yes, yes. Essentially, what is...
One of them in the usual sense, just
Yes.
as singular homology, and the other
is the cohomology of the loop space.
Yes.
Yes. So, in some sense, there is some evidence, actually,
Yes.
that it is an analytic version of Floer homology.
Yes.
Okay.
Of course.
So that this is, in some sense, a candidate to be the analytic version of Floer homology.
Which is well known for some 40 years, the chance path integration which is obvious candidate to be the Ragni theory of the loop space. Well, if you wish to have torsion invariance, you can consider the equivariant version of this. Does it appear here in some way?
Well, I mean, you see, if you look precisely at what the forms
Yes.
I described
Yes.
that you integrate on the loop space,
Yes.
they are actually Chern. They are Chern forms.
Yeah. Oh.
They are exactly of this
Exactly.
kind. Okay. So the bridge is actually done through this.
Yes.
Because in effect, what you integrate are
Just
forms
explain
Chern.
to formulas,
Yes.
Exactly.
Yes. So that's exactly what you say.
Okay. Thank you very much.
Thank you.
My question is, you assuming some non-degeneracy condition.
Of course.
You didn't make it explicit, but you need
Of course,
it.
I did not make it explicit because in some sense, I mean, the work is still, the work of really connecting to these critical points of the energy function or whatever it is still not done. But it is true that the conjecture of Fried and all conjectures of this kind are actually valid for symmetric spaces where there is some negative curvature, which actually ensures that the Morse function that you're looking at behaves itself is a Morse function and behaves properly, right? So in effect, the conditions of validity, I mean, the thing in some sense is self-consistent, right? When the conjecture is even formulated, not to speak of when it's already proved, it's only proved under such cases where actually the energy functional is a nice Morse function.
Okay. Thank you.